something that's relevant to sampling is the error that goes along with sampling. Because as you all know, there is always error anytime there's research, and in terms of gathering data and analyzing data, there's always going to be error of some kind. So this is just another type of error, and it's called random sampling error. And this is essentially the difference between the sample statistic and the true population value due to chance. So anytime you're getting a statistic about your sample, and it could just be like proportions of some kind of characteristic, or it could be, a relationship between two variables. But anytime that's going to be a sample statistic. You're getting information based on the data that you gathered from the people you actually talked to. So then random sampling error is the difference between that statistic that you get based on the information you actually have and the actual population value, which is really what we want to be able to generalize to. And so, if we get, that there's a correlation between two variables in our sample, that's great, that's what's in our sample, but what we really want to say is that, well, that is then the approximate correlation value between those two same variables in the actual population. That's the one we really want to talk about. So the random sampling error then is the difference between what you get in your sample based on whatever statistics that you're going to run and what those same values, those same statistics are in the actual population. Because they're never going to be exactly the same because there's always error, but hopefully that error is reduced as much as possible, and so it's as close as possible to the actual population value. And so then this begs the question, well, is it actually sampling error, or is there some kind of bias involved? So random sampling error is kind of what just happens because of something that we can't really control. It's just natural fluctuation and variation in our sample compared to the larger population. However, there's systematic error as well, which then is really more of a bias. And so this would be differences between our sample and population because of some problem with the sampling method. So we don't actually have the representative sample we thought we did, or it wasn't as random as we thought it was, or whatever the case may be. And so major sources of systematic error in probability samples in particular include really bad sampling frames. So, we thought it was a good sampling frame, we thought it was randomized, or we thought it was actually, a sampling frame that included the entire population, but it didn't. But also non-response. So think about, okay, we can get this wonderful random sample from a sampling frame, being the list of everybody in our population. But we try to get people to come in and they say no. And, we want to interview them and they say no. Or we want them to do a survey and they say no. If we get too many of those people saying no, we can have the best sampling procedure and have come up with the best list of names. But if 75% of those people don't want to participate, and ethically we cannot force them to, and we can't even really try to convince them to in any way that would border on coercion, then we're going to have really low response rates, which means that original sample that actually would have been really representative of the population now is no longer representative because we only got a quarter of the people to actually talk to us. So that would be systematic error though. And so random sampling error is more what happens even when everything is going right and your sample did go the way you wanted it to. So statisticians then will estimate the probability that the sampling statistics, so what you got in your sample, is representative of the larger population, and they use what's called a sampling distribution. So what that looks like, here's an example. So it's essentially the sampling distribution is the distribution of a statistic across an infinite number of samples. So basically what it is we take one sample, and so let's say we're doing something like, height, make it easy. So we're getting everybody's height from this sample, we plot it, and we come up with the average height. All right, go back to the drawing board, draw a completely different sample, get everybody's height in this completely different sample, plot it out, find your average. Let's go back again, draw a completely different sample from the population, get everybody's height, and find the average from that sample. So a sampling distribution then is basically doing that a bajillion times, enough to get, so then you end up plotting all of these averages. So then you come up with the sampling distribution, which is a plot of all of the averages from all of the samples that were pulled. Now, this doesn't mean that somebody is going out and doing this all by hand. There is software that does this, and there is algorithms that do this. But that's kind of the idea of what it's doing, is it's basically taking a population and drawing random samples from that population, measuring that characteristic and finding the average for each sample, and then we plot each of those averages. So then we're going to have a whole bunch of averages that we plot, and that creates this nice, beautiful bell curve that is what we call the normal curve, a bell curve. You see that on like every sampling distribution. Because when you draw enough samples, this beautiful bell curve is just naturally going to happen. And so then this tells you like, so, you know, we have, looks like 50, 100, 150. So like we have like 150, say this is height we're talking about. And so like that are at like 5.5 or whatever, or 5.7. And so that's like most of the averages are right around there. And so we have 150 or more averages from different samples of the same population. And so 150 times that a sample was drawn, it had an average of like a height of 5.5 or whatever. So a sampling distribution is plotting all of those averages and then naturally getting that bell curve that is going to happen. And then that tells you where the most likely average of a sample should be and what you're going to get most often. And so if you get a sample and, for example, and your average is way up over here in one of the tails, then it can happen because it happened in the sampling distribution. It just doesn't happen very often. And it's really unlikely to happen. So that's what a sampling distribution is. So, and here it is kind of explained a little bit more in words, is a hypothetical distribution of all random samples that could be drawn from a population. So it's that hypothetical distribution of all of the averages that we could draw from a population. So estimates then, we use the sampling distribution to estimate margins of error, or what are called confidence intervals. So you're going to get a sample statistic, and then there's going to be a confidence interval around that. That confidence interval is based on the sampling distribution. So it's based on the likelihood that that actually represents the population. So these confidence limits then are the upper and lower bounds of the confidence interval. So you're going to have your sample statistic in the middle, and you're going to have the upper part of the confidence interval, so the upper confidence limit, and then the lower confidence limit. And so that basically tells you how much confidence you have in the estimate. Because if you have a really big confidence interval that basically covers almost the entirety of possible values of whatever the variable is, that means you have like no confidence in your sample statistic. If you have a really small confidence interval that you're like let's take height, and you're like, well, here's our sample statistic, plus or minus like an inch, let's say, for height. That's a really small confidence interval. So you are really sure about your sample statistic and that being representative of the larger population. So some very commonly used confidence intervals are 95% confidence intervals, 99% confidence intervals, and 99.9% confidence intervals. So a 95% confidence interval means that I am 95% sure that the real population value lies somewhere in this interval. So I'm 95% sure. If I want to be more sure, if I want to be 99% sure, I have to increase that confidence interval a little bit, because now I'm more sure. My confidence interval is bigger, but I'm more sure that my true population value lies in there somewhere. And if I want to be 99.9% sure, I can make the confidence interval even bigger to be more sure that my population value is somewhere in that confidence interval. Remember, your sample statistic is always right in the middle of that, because that's what you got from the data that you actually ran. But then the confidence interval is on either side of that. And the bigger it is, the more confident you can be that your population statistic is in there. So then if you have a 99.9% confidence interval that is also still relatively small, you are like really sure that whatever you're saying for your sample is true for your population as well. And this can be just like looking at one variable. It could be looking at a relationship between two variables. Or some kind of pattern that's in your sample. That confidence interval is going to tell you that you are really sure that that thing is also true in the population. So this sort of equates to p-values. So, and this sort of ties into inferential statistics, which we'll get to in sort of another video. But when we look at p-values, So to say a p-value of 0.05 equates to a confidence interval of 95%. So a p-value of 0.05 means there's a 5% chance that we're wrong. So that means we're 95% sure we're right. Or a p-value of 0.01 means there's a 1% chance that we're wrong. So we're like 99% sure that we're right. Whereas a p-value of 0.001 means there's like a 0.1% chance that we're wrong. But we're like 99.9% sure that we're right. And that's about as big as you can get, about as sure as you can get. And then the last thing to sort of talk about is what's called units of analysis. And units of analysis are basically the level of social life that we're focusing our research on. So typically, unit of analysis would be people, would be individuals. That's the most common one. And that would mean that your sample consists of people that you talked to or you surveyed or whatever. But sometimes you could have groups. And so your unit of analysis will be groups. So maybe you're comparing, say, different NHL teams on, some kind of statistics or something that, some kind of like win percentages or whatever. And so your unit of analysis would be teams, would be NHL teams. Or maybe you're comparing cities if we're comparing crime rates or something. And so it'd be, let's look at crime rates and see how it relates to like poverty rates or something like that. And we're comparing across a whole bunch of different cities. Then our unit of analysis would be cities. So the most common is individuals, but it doesn't mean that that's always the case. And so this is very much related to the unit of observation. And this is the cases that you're actually getting information from to get information from within your sample. And so typically the unit of observation is the same as the unit of analysis, but sometimes we might get information or we might get information directly from, say, individuals, but then we end up using that to talk about the groups that they come from. And although we have to be careful about this, because there are two common fallacies that can happen. And sometimes this happens if our unit of observation is not the same as our unit of analysis. And so if we're not careful, we can sort of have these one or two of these fallacies happen. So these are two very common fallacies. And the first is ecological fallacy. And this is where you gather information at the group level, and then you make inferences about individuals, and you're doing so erroneously. So for example, if we determine that the average income for an area is, say, $30,000 a year, that's the average income. If we then assume that somebody from that area will likely have an income around that average, that could be an ecological fallacy. If, say, for example, there are two different parts to the neighborhood with averages at like $10,000 a year in the poor area and $50,000 a year in the other area, that's going to make the overall average somewhere in between there, right around the $30,000 a year mark. But no one person is actually near that overall average. So you have people making really low where their average is around 10,000. You have people making more where it's around 50,000. And so overall the average is 30,000, but nobody actually is at that 30,000 level. So it would be ecological fallacy to say an individual from this area probably makes $30,000 a year. That would not actually be true in that situation. Or for example, if I measured math scores of everyone in a class and found out that that class was, had the highest average at all MSU institutions. Then I might see one of those students later and be like, oh, you were in that class. You must be like a math whiz. Not necessarily. That could be the dumbest person within the Montana University system, and they're the dumbest student, but they just happen to be in that really smart class. So that would also be an ecological fallacy. And then there's the reductionist fallacy. And this is where you gather individual level data and then make inferences about the group. And this is at the core of a lot of sexism, racism, overgeneralizations. So for example, a woman crashes a car or makes a driving mistake and a man sees it and thinks, oh, women are all terrible drivers. No, that's a reductionist fallacy.